And now we're going to hear from George Minassian, who's founder and CEO of Crossbar. They produce high-performance, high-density, resistive RAM technology, and this company is leveraging resistive RAM to deliver faster write performance and lower power consumption, all on chip. Before founding Crossbar, he was VP of System and Software Engineering at Spansion. Prior to that, he was Director of Wireless Engineering at Advanced Micro Devices, AMD, and their Advanced Architecture Lab, managing teams working on CMOS, chipsets, and reference designs. And continuing on our water theme, Dr. Minassian tells me that he likes swimming and that he was on the UT swim team. So with that, we'll invite Dr. Minassian to speak. Thank you.
Good morning. I'm George Minassian. I'm CEO of Crossbar. It gives me a pleasure to talk to you and tell you about how resistive RAM will turn big data into big dollar. We found Crossbar in 2010. And when we set up a startup in memory, you want to set some big goals or your toast. And the one we set was, we'd like to get 1 terabyte in the size of a postage stamp in a chip. Within 2 years, we got a huge amount of publicity, and this was a good, nice goal. But we really didn't do this. We really didn't do this to have the bragging rights for the largest density or fastest speed. The reason we did this, we took a look at the applications and our customer base and what it takes for our customers to be successful. And we found out that for them to be successful, they need to be able to process huge amount of data. They need to be able to store them, retrieve them, and be able to analyze them quickly. And if they're able to monetize this, then they will be successful. And that's where our technology started to develop. But before we continue, let's talk about why 1 terabyte on a chip is important. I'm not going to be the first one or the last one that's going to tell you in this conference or in this month that data is the new oil. It's about making money as you harvest from this data, and that's where our technology will help the industry. It doesn't matter if you're making stock trades, which frequency and time is extremely important. It doesn't matter if you're putting Facebook pictures in front of your users. It doesn't matter if you're trying to prevent a pedestrian walking in front of an autonomous driving car. All of these require a huge amount of data, and processing of this data is the heart of how you would harvest the money from this big data. This requires complex algorithms. This requires real-time processing and access to huge amount of data at a very instant and fast fashion. Facebook, Microsoft, Google, they're creating huge amount of information. This is facial data, location data, applications, new games. Internet of Things is growing huge. The self-driving cars are here now. We keep hearing about them all the time. And cloud computing is really pervasive today. Yet, the business of how we extract data from this and turn this big data into money is just starting. New innovative designs and architectures is the key to enable this extraction and make sure this is available as we wear those devices in huge computing environments and in the systems. It's all about data, and it's all about money and making money from this data. For our customers to be successful, they need to have 4 things: access to a huge amount of content, making this right content available in the right time to the user, having new algorithms that will extract this information and do this very quickly before the next guy that they're competing against does it for them. The system that needs to be in place to help our customers, though, is changing. It is well known that the Ohm's law is kind of slowing down. And because of that, we all have experienced the slowness of introduction of microprocessors or the cycle. It really isn't as fast as it used to be every year, new processor, new systems. But really, it's not about compute and computing anymore. It's about bringing computers and memory together in an integrated fashion that you have the data and the processor, and you're breaking the barriers that have existed in the standard architectures when you have standard buses and standard ways of doing things. We believe the resistive RAM is the basis that allows this new paradigm of computing and computation to take over, and that will enable the artificial intelligence that we're all seeking to extract and use this data effectively, and also monetize it for our customers. If you look at the standard architecture, and I've got that picture here for you, this is very advanced architecture as it goes. It has 256 cores, local memory, and some local cache, of course. Then externally, it's connected to a bus that goes to a fairly standard memory. You have some embedded flash, some NOR-type flash, as well as gigabytes of DRAM. Very typical, very high-performing memory. When we started Crossbar, the 1 terabyte was a big goal for us. We thought it was really huge. Little we knew that that really isn't the real target. The aha moment came in when we said, hey, no, we not only have 1 terabyte, but we can also combine it with the same logic if this terabyte can be embedded on the chip. And that was the real power to continue to generate not only the capacity, but a better way of integrating that capacity with the compute engine. I'm now convinced that we can put that 1 terabyte huge amount of density on chip where the processors are needed and avoid all the complexities that the buses have. So in this architecture, you have the memory where the processing is, and you can avoid going through the standard buses that, although we are making them faster and faster in the industry, they still become the bottleneck for processing and computation, and they take huge amount of energy as the signals go through them. In this architecture, you have the embedded storage, the storage element of the memory, and the memory for processing and execution very close. What that does for you, it relaxes the hierarchy of memory, and it puts memory right where the processing power needs to be. And that allows new ways of harvesting the computation with the memory right next to it. The system performance gets better. You don't have to have this I/O that is also a source of wasting a lot of energy because the buses are now avoided. It's right there. Now, for this memory to be on the chip, it needs to be CMOS compatible. And I'll tell you more about our technology, why it's right on the top of the CMOS. Actually, that's how we started from day one. Having memory and processors right next to each other, there are new ways you can do things that weren't as obvious or possible before. Actually, we did this in industry, but it was cumbersome. Instant on, very low power, extreme security when these devices don't have to exit the system and get into the buses, and it's all inside the device monolithically. That brings you new opportunities. Well, I'm also convinced we can do standalone memories, high density with our resistive RAMs, and processors are coming up with huge amount of power and new brand buses that overwhelm the speed of NAND, although we come up with new NAND architectures that overcome the bus limitations, but they add a lot of complexity. With resistive RAM, the power, processing, and speed, and the densities, we can also serve that market and create systems that will give you huge IOPS in terms of volatile memory, DIMMs, and or servers, and we'll talk about that under NDA. You're welcome to, if you have passed to our special booth area, you can see some of this in operations and demo. More about that later on. If you have all of this integration with the performance and speed we provide, avoiding the buses that get in the middle by creating more power drainage for you and delays. And by integration, the overall system cost is a lot simpler. You don't have the noise signals and expensive board space with all these antennas for other devices that are present that you have to worry about it. All of that signaling is integrated inside the chip. It allows you to do very new architectures and get into the new segments. Let's look at what's the underlying architecture that allows all of this to happen. If you're using flash, and we use that in previous companies I worked for 20, 25 years, they use transistors for storage. And with transistors, when you shrink, they tend to be more leaky. And if you have leaky elements as the basis for your programming or storage, for memory, that's not very good. So the flash technology is about 30 years. So look at that, it's really big adult. And as adults go, if they want to grow after at age of 30, I think they just grow in one direction. And that's growing out. And that's exactly what flash is doing. The analogy holds because they are now growing in the Z dimension. And we can also grow in the Z dimension in Crossbar. However, we are looking at another dimension that I'll tell you about a little bit later, and that's the N dimension that gives us more freedom. If you look at all the companies that are here today and this week, they are using the all-flash technology based on transistor, and they are growing in the Z dimension. This whole conference is about the flash stacking and growth in the Z dimension, and the kind of products that are being announced with these names in them today. Now, besides the limitation of growth, the other thing that is obvious is in these technologies, because they're based on transistors, as they become smaller, the noise level increases, the controller complexity is very huge. So yes, we have more storage with fewer transistors. The problem, of course, is you add more transistors to extract this information correctly and make sure the cell data, which is now on the borderline, is extracted and calculated. This was one of our biggest headaches in the last two companies as we were producing massive amount of flash. So the complexity of the controller goes up, and with that, the overall budget and system power budget has never relaxed. It just stays the same, whether you used to spend more of that in the transistor for storage, or now you're spending more in the algorithm development. The end balance is you're still wasting a lot of extra transistor. We are not the only ones that have recognized this, by the way. If you look at all of our contenders and competitors in this place, they are working for technologies that will be alternative to resistive RAM. But as much as I try, they don't share those details with me. That's their secret, and I'm sure you can get those secrets from them directly. I will focus on what we're doing, and with NDAs, I'll be able to tell you everything about current and future technologies. Now, the way our technology is different is ours is based on nanofilaments. Very simple 3 layers, metal on the top, some resistive open amorphous material in the center. Some of these are published already, and a conductive material at the bottom. This is cross-section of 2 wires, and every cross-section has one of our cells. So you can't get any smaller than that. Cross-section of 2 wires is the smallest geometry in the fab you can get to. And you can put these memory elements exactly where you want them. Huge density. Voltage is what turns this device on and off. It's not based on heat. It's not based on temperature. It's not based on magnetic powers, none of those. So the interplay between the cells is 0, minimum. Huge endurance for temperature. We have seen, initially surprising to us, that temperature doesn't really impact this structure, which is good for us and our customers and the applications they're pursuing. Now, with these devices, we have been able to produce speeds that are, read-write speeds that are about 1,000 times faster than NAND. The power consumption is 1/20th of what we have measured. We really haven't seen anything this low. One of the strategies we had that we should have done from the beginning. We underestimated how little power it takes to move these cells around. And the added circuitry we have put in place through the last few years is to address the smallest amount of current that requires and limit that such that it turns on the transistor and the rest aren't wasted. It turns on the cell, sorry, and the rest aren't wasted. So that realization has the extra benefit that as far as power goes, these devices consume the smallest amount. The endurance and cycling for these devices are very nice. We get 10-year retention with 100,000 cycles. This is just one example and where we have set the parameters. And in some set cases, we can optimize it for one extreme or the other. But so there are a lot of ways to improve this even further. In the very near future, we see our path to below 20 nanometer with our technologies. And there are a lot of other companies involved in this. So under NDA, I can describe some of that for you. And as I mentioned, our technology uses standard CMOS material in the fab. And integration with CMOS was from day one how we did anything. So you had the CMOS controller at the bottom, the memory on the top. So all of this takes place not in a special expensive memory fab, but in generic CMOS factories. Let's talk about the N factor. It's a little bit complex engineering, and we can dive into that, but I'm trying to use an analogy to it to maybe explain that faster. Imagine an orchestra, and imagine a special violinist that you really want to listen to and have the crisp noise and the brightness of this instrument. For that to take place, the rest of the instruments have to be very quiet. And that is the trick for our Crossbar N technology. We have a technology that every built-in cell, when it's not addressed, is extremely quiet. So the person who wants to talk to one of those cells out of 4,000 could select a specific cell and listen to it and talk to it. And the rest of the cells are not getting into the conversation. Therefore, we have rock solid communication between one transistor and one of 4,000s. We can even do more than 4,000, but that's where we have set the limit for the first sample, some of which you can see in our enclosed booth under NDA. Our patented selector has received a lot of attention in the industry. We were in IDM not a few months back. We talked about the details of this technology, and there are a lot of people that were saying, well, this is very hard to see how it's done. We brought them to our lab, and they have witnessed that for themselves how it is implemented. You're welcome to take a sample that's a fully working silicon in our demo area in our booth. This allows huge amount of density that the one transistor, one resistor element will not allow to be combined in a very small area. You're not limited by the size of the transistor anymore. You can put 4,000 and even more cells behind each one of those, and that gives you a new dimension, the N dimension, in terms of increasing capacity while maintaining the performance and while enhancing not impacting the system behavior. In the DIMM that we are planning to introduce with this technology, you can have 100 times faster reads, 1,000 times faster writes. You can have 24 million ops in a 4 terabyte non-volatile DIMM, and that's just to start. In upcoming conferences, we plan to show a system. There is a prototype of that here that gives you 2 giga-ops, IOPS, in a 1U or 2U server. Initially, I think we won't worry about the size of the server, but it will be a 2U server, and we'll demonstrate the technology and its performance. So where are we with the progress? We've been in business for 5-6 years now. I'm very proud of the execution that we have demonstrated with a small team. Less than a year ago, we announced a partnership with the world's leading largest fab in China. SMIC partners, my partners are here. Many thanks for their round-the-clock help as well. We have produced Crossbar 1 at 40 nanometer, and we're starting to talk to customers and license that product for IoT-based devices. We have delivered on the embedded process, and with our partnership with SMIC, we continue to excel on the execution of that. With that product, embedded, you can have very fast performance. Our reads and writes are super fast. It's available at 40 nanometer integrated. There's not very many 40 nanometer embedded memory, as you know. And this operates in a very wide temperature range, uses only 2 volts to read, write, or program. It's 10-year retention, 100K cycles from get-go. We have 8 megabyte blocks available, and that's sufficient, and you can have multiples of those in your SoCs as you produce them. This powers the IoT applications very nicely. Going forward, if you look at the Crossbar N technology, we have produced a sample of that. We welcome you to come a close look under NDA. And with that, you can have non-volatile DIMM and abilities to introduce huge amount of IOPS, high density, high performance, without sacrificing speed. Read-write is exactly byte-oriented, so you don't have the overhead of block orientation, which the NAND requires. So even from system standpoint, it's very easy and friendly to use. We expect in future shows to have models and system models of that, but you can take a quick look at what is available right now. That technology, we are working very closely with partners. Unfortunately, under NDA, I can't tell you a lot more about this, but we have our path with multi-million-dollar contracts signed that takes us below 20 nanometer, and we were proud of the partnership. It took us several months of close discussions to get to that point. So soon, you will see also huge densities at a very small node below 20 nanometer from us. And what that does, when we started the company, we thought, the 1 terabyte was a huge goal. We know better. The real big goal and the aha moment for us is to put the high IOP-based RRAM in a DIMM and have giga IOPS in servers with our technology. We believe in a future that is based on zettabyte of data. There are various publications that talk about 44 zettabytes available in 2020. That's the future we believe in also. We believe that data would be hierarchical. We believe access and information extraction from data would be as critical and as important an element. And for that, you need to have a new architecture. Extending more horsepower on existing compute architectures and memory architectures is not going to get us there. Combining and blurring the line between computation and memory and providing memory that relaxes the hierarchy of your system, doesn't sacrifice the performance of the system, gives you byte addressability, which is common to use for memory access versus more complex situations, will allow you to harvest huge amount of data and will fuel the industry as it goes toward this huge data extraction. We believe with Crossbar technology, we will enable you to make money from this big data. We have a booth here for some that haven't visited us. We invite you, that's booth number 219. We invite you to come take a look. We have our samples from our SMIC partnership, 40 nanometer embedded devices, multiple games and setups that we have there. We welcome you to stop by and look at it. And also under NDA, we can tell you about the Crossbar N technology and samples of that and status of that and plans going forward. I thank you for your attention and thank you for your time.
So, Dr. Manassian, we have a few minutes for questions. Do you want to take questions, or should we wait until later?
I would appreciate if we take the questions in the booth. We have the setting there, and the people can stop by. I know you have already done that. So that might be a better setting for questions. Thank you very much.